And we're back. Welcome back from the weekend and happy Tuesday. Today we'll be switching gears, looking at conditional probability and Bayes rule. But before we begin, let's go over some administrative bits. The reading has changed. It will be this PDF on conditional probability and Bayes rule. There's the URL. It's also linked through the course Blackboard. The midterm will be due a week from today, 20th of October at 4:30 p.m. You'll be reading a publication and analyzing it, comparative analysis, nonlinear dimensionality reduction, techniques for breast MRI segmentation, and you'll be each giving a 15-minute presentation. So that's a week from today when class begins at 4:30 p.m. So why don't we begin? So we talked about the pipeline concerning the anatomy of a pattern recognition system. And we started out with our discussion of sensors. And for that, the example we used was computer vision, namely image formation and the camera model, as well as image representation, specifically RGB color space. And this was not indicative of all the different image representations. It was just one particular image representation, an example of the raw information that comes from our camera, namely our sensor. And then we talked about feature generation. And for this, we looked at image intensity surface as a representation of an image, be that in black and white or in color. And in color, we had 3 different color channels, each one of which implements an intensity surface. We talked about the convolution operator as a way of approximating the derivative that gives you the gradient for intensity. We did that along X and Y, and we can use that to get the orientation of an edge as well as the edge magnitude. We looked at appearance-based features. We looked at color and shape in particular and discussed the concerns about the specificity of your image content depending on what your choices were for this appearance-based color representation. So then we looked at feature selection, in particular a number of dimensionality reduction techniques. We looked at principal component analysis, classic multidimensional scaling, ISOMAP and LLE, where ISOMAP and LLE are nonlinear methods, and PCA and MDS were linear methods. In each, we are looking to calculate a change of basis, some of which use distance matrices or affinity matrices, and in each case, we produced a orthogonal basis set that re-expressed our data through some form of diagonalization. So now we will move our attention to classifier design, and this is the method by which you create, train, and build your classifier. And some of the questions here to kind of give you a reminder of some of the concerns. How do you design the optimal or best classifier? What does optimal even mean? And then lastly, partitioning your feature space with a so-called decision surface. But before we do that, let's have a reminder. We talked about the anatomy of a learner. We said there are parts of your learner that you do not have control over. Those were the boxes in red. And there are other parts that you do have control over. Those were the boxes in black. And so in particular, we're going to take a look at the hypothesis set and the learning algorithm. And we said that the learning algorithm searches through your set of hypotheses looking for the notional best one. Now, what does best mean? Okay, well, we'll get to that. Here we gave an example of an image data set, and in this we had 2 categories. We have cats and we have dogs from images, and we assumed that we had a 2-dimensional feature space with texture as the first feature and shape as a second. We just illustrated this in 2-dimensional feature space representation because it's easy to demonstrate the concept on a slide. And so we have in our hypothesis set a set of candidate formulas, and you make an educated guess as to the type or form that this hidden target function will take on. And now your learning algorithm's responsibility is to search through the space of hypotheses for that single hypothesis that most closely mimics the assignment of categories to feature vectors. And so this is the one that has the least error. And we also include in the things that we control the error measure. And the error measure is evaluating the performance of your current working hypothesis on one of the candidate formulas of some form or from some family of candidate formulas. And so we're now looking through this error measure and this search implemented by the learning algorithm for this best hypothesis, the one that has smallest error with respect to the assignment of labels or categories to input feature vectors by the target function. And so in this example, we plot our data set in feature space in 2 dimensions, and we have x1, x2, x3. Let's assume they are cat images based on the content, and then x4, 5, and 6 are other images that are not cat images. They could be dog images in the example that we carried earlier in the semester. And so now we know that a line can separate these points, but we don't know which is the best line. So we initialize with some starting hypothesis. We evaluate the error with respect to the ground truth target function. And in this case, x2 and x3 are correct. x1 is an error. x6 is incorrect. It's an error. x4 and 5 are correct. So now we update our hypothesis with our search, our learning algorithm, and we now select a new hypothesis. And this is a different line. You'll notice its slope and y-intercept are different. And we keep doing this search, re-evaluating the error, trying to find the hypothesis associated with the smallest error. Once we do so, we stop, and this learning algorithm converges, it halts. Now, if it didn't halt in a certain amount of time, you could certainly use different approaches, number of time steps to decide when to stop your search for your learning algorithm. You could use some change in error becomes negligible, a whole host of halting criteria, but nonetheless, this learning algorithm stops at some juncture. And so we output now final best hypothesis, which we'll call G. And so G is that little h from your hypothesis set associated with the smallest error when the learning algorithm halts or comes to convergence. And so we output this final best hypothesis, G. G takes an input feature vector, in this case in 2 dimensions, because it's 2-dimensional feature space, and it outputs a labeling Y. In this case, our label is one of 2 categories, cat or non-cat, cat or dog. And so the particular type of functions, hypotheses, the form that we're going to look at is a category of functions, namely probabilistic classifiers. And so as a function, probability is nothing more than a special function. It inputs some input and it outputs a number, and that number is between 0 and 1 on the closed interval on the real number line. And this number we'll interpret as being the probability that given a particular feature vector, the probability of one class label versus another class label, cat or dog, +1 or -1. And so because a probability is nothing more than a special function, of course, our hypothesis set is a set of functions. In this particular case, with the probabilistic classifier, we're going to look at a hypothesis set consisting of probabilities. But in order to do that, we need to develop and review some machinery associated with probabilities. Specifically, we're going to look at conditional probabilities. Okay, so let's begin with a little warm-up. We have events, and an event in the case of a probabilistic classifier represents an instance of a feature vector. And of course, as a feature vector, these values for each of the features, they are considered to be the assignments of values to random variables. And so each position or each feature is a random variable, and therefore a feature vector is just a vector of random variables, the collection of which are defined by a joint probability. And so we begin with an event, which is an observable outcome resulting from some action. And so that action is the action in place by the sensor. It gives you some feature vector. And this action is called a trial or an experiment. And so we have this thing called a sample space, and the sample space represents all of the possible instantiations of the random variables, events for a given system. For example, if you're talking about a coin flip, the observations sample space is heads and tails. If you're talking about, say, the roll of a single die, it has 6 sides. The sample space are all the possible events 1 through 6. Now, certainly they exist, but it's a little bit more difficult to think of. For example, if you have a 620 by 480 image in RGB color space representation, the sample space is absolutely huge. You have 620 by 480 by 3 bytes, right? So a byte is 8 bits. And for those 3 bytes, you have the red, green, and blue color channel. And for each one of those 620 by 480 by 3 8-bit positions, you're going to have 620 by 480 by 3 numbers, each features, each of which can have a value from 0 to 255, representing the saturation for each one of the RGB color channels for each pixels in a position of those 620 by 480 coordinates in image coordinates. And that's just low resolution. That's VGA. We're not even talking about high def or 4K or much higher resolution images. And so these sample spaces, whether you're dealing with images or coin flips, you can absolutely talk about feature vectors as being drawn or an instantiation from some very large sample space for something like an image. And so your events, your particular observations, they occur at some rate, and this rate is a probability. In the case of an image, it's a big joint probability. Even when you produce features, well, all that feature generation, feature selection is doing is reducing the dimensionality. And so in effect, it's reducing the size of the sample space because you have a smaller number of features. And so we care about this because we want to evaluate the structure of our systems, and that's what probabilities are doing. They're describing the rate at which you're going to see certain instantiations of your features over other instantiations of your features. And so we're going to generalize this idea, random variables. Sometimes we want measurements over events, and a measurement could be an image intensity gradient. It could be edge measurement, but nonetheless, we measure events or sets of objects, and these outcomes are uncertain from which we take our measurements. And so one thing we might ask is how many objects do we have, or how often does a particular object or set of objects occur within some raw feature space or event-based description. So we're going to motivate this with an example to develop the intuition, and then we're going to get into the conditional probability, what it's doing, and then end that with a definition and example using Bayes' rule and why Bayes' rule is important. So we're going to define T, and T is just going to be a random variable, and let's assume that's going to measure the number of tennis balls of a given color that you pick from a bin while blindfolded. Now, this while blindfolded part is particularly important. It means that you're not going to prefer any one bin over another or any one ball over another. This means that there's no preference, so each of the tennis balls are equiprobable as far as their chances of being selected when you're going to pick a ball out of the bin. And so the general form is you have your random variable. It's going to take on a value, that's your measurement, and you calculate this by looking at the number of items of interest that have a certain value that you desire, divided by the total number of items that you have that are possible. And so here we have our bin, and some of these tennis balls are yellow tennis balls, and some of these tennis balls are green tennis balls. And so our random variable T is going to measure the color of the tennis ball that you could pick. And so, of course, I have to show this to you on the screen, but you can imagine being blindfolded, you're not preferring any one over another. And so if we want to know the probability of selecting a ball that's yellow, well, we have a total of 4, 8, 12 tennis balls. And the yellow tennis balls, if we were to count them, that would be 7 tennis balls. So the probability, number of items of a certain value, of value yellow, is just the number of yellows, so that's 7, divided by the total number, that's over 12. And likewise, if we do the same thing for green, well, again, the total number of items is 12. That hasn't changed. But the number of items that we desire for a particular value for that green color, there are going to be 5 of them, so that's 5 12ths. And there's our answer. And so this is the general approach that we use when you calculate probabilities. We have the number of items that we desire over the total number of items that are possible. And so we're going to draw another example. In this case, we're going to have more than one attribute. We have a bunch of tennis balls, and these tennis balls, let's imagine now that they're all yellow. And we're going to group these tennis balls together, and we're going to put a label on each one of the bins associated with these tennis balls in a particular grouping. And so some of the tennis balls are from bin that we label number 1, right? So you can imagine taking a black magic marker and you're writing 1, or a blue magic marker, you're writing 1 on each of these tennis balls, and they're originally from bin number 1. And let's say we have tennis balls that have a bin number 3, so you're going to write 3 on each one of the tennis balls from bin number 3. And then likewise, you're going to do the same thing with tennis balls from a bin labeled 5 and a bin labeled 7. So we have 5, 5, 5, 5, and 5. And then we have here, this bin only has 1 ball in it. We're going to label it 7. And so now we're going to take this experiment and we're going to take each one of the balls from the respective bins with the magic marker with the bin number written on them, and we're going to dump them all into a bag, and then we're going to have somebody blindfolded pick a ball from this bin. And so in this, what is the probability that the ball that you pick has a bin label number 3? Now, of course, our labels are 1, 3, 5, and 7. So what do? Again, by the scheme, we take the total number of balls that have a particular value. That's going to be 10 balls. So 3, 6, 9, and one more is 10, have a label number 3 on it. And the total number is going to be 20. So again, going back to first principles, the probability is the number of items desired of a particular value or this particular attribute. So that's the bin label 3 over the total number, that's 20. So that's 10 over 20, which is just 1 upon 2, or 50%, or 0.5 probability. So now we're going to change this up a little bit. Now we're going to introduce different colors. We still have the same scenario from before where we associate these bin labels on each one of the balls as depicted in the figure, but some of the balls are going to be colored green. So in bin number 1, we have 3 balls that are yellow, 1 ball that's colored green. In bin label number 3, they're going to have all 10 balls are yellow. In bin number 5, 2 of the balls are green and 3 of the balls are yellow. And then lastly, in bin 7, with that single ball, it is labeled green. And so we have 2 attributes here. We have the bin label, that's bin, and that bin could be 1, 3, 5, or 7. And then we also have a color. That color could be yellow or green. So now we're going to ask a different question, and it's the same scenario. We have both bin labels in magic marker written on each of the balls, and we also have balls of different colors as depicted here. We're going to dump them all into a bag, blindfold you, you reach in, and you grab one. And one of the questions we want to ask is that the color of the tennis ball, what's the probability that you're going to pick a green one? So going back to, again, our first principles, the number of items of a particular value. So we have 1, 2, 3, 4 green balls, and we have a total of 20. So that's 4 divided by 20, which is 1/5, or 20% probability, or 0.2 probability. Okay, so now what if we aren't concerned about all the balls? We're concerned only about some of the balls from some of the bins. Now imagine you saw me when you were blindfolded. Hey, Dr. Holness, he didn't put all the balls into the bag before you were blindfolded. He only dumped out a certain bin number. So you use the framework of conditional probability to do this, and you can also think of this semantically, or how it behaves, as a type of probability with filtering. And so the terminology is conditional probability, and the semantics, the syntax here is probability that some random variable equals a value, and this vertical bar given that some other variable, random variable, takes on another value. And so how you pronounce this is the probability of the left-hand side of given the right-hand side. So in this case, probability that variable 1 takes on a value, given that variable 2 takes on another value. And so behaviorally or semantically, you can think of conditional probability as a kind of probability with filtering. You're going to filter out objects for which variable 2 is equal to the other value. And when I say filter out, I mean you're only going to consider. So what does this filtering out do? It limits what I'll call, or changes your universe of consideration. And that universe of consideration is going to change what it means when we say the total number of items. And that was the denominator. We said the number of desired that have certain value over the total number. Okay, total. And so this universe of consideration talks about the denominator here. And so when you perform this filtering function, that filtering is only going to consider objects for which variable 2 is equal to other value. So that means this denominator is going to change. It's going to get smaller. And you'll see in general that when you have a condition, something known to be true, that's going to increase the chances of that expression or that part of it in the numerator what's desired. Because by decreasing the universe of consideration, this total, this denominator, going back to first principles, the probability or your chances are going to increase. And so now, once you filter out objects for which variable 2 is equal to other value, your universe of consideration is updated, you then calculate the proportion of objects for which variable 1 is equal to value, and that's the desired. So it's the desired over this new total as a result of reducing your universe of consideration, for i.e. considering only those objects for which variable 2 is equal to other value. Okay, so let's take this example that we had from before. You have bin number 1, 3, 5, and 7, and the labels for each of the balls within these bins are going to have a label 1, label 3. So all of these have a 3 written on them. 3, 3, 3, 3, 3, and 3. These have 5. And that last ball in bin 7 has a 7 written on it. So we have two attributes. We have both color. That's going to be random variable t that's going to measure color. And then we have b, which is the bin, which is the bin number written in magic marker. So here we have green color in bin 1, yellow color bin 1. We have yellow color bin 3, no green color bin 3. We have green bin 5, yellow bin 5. We have green bin 7, no yellows for bin 7. So now we want to know, for example, what is the probability that when you reach into that sack here, I'm going to take these balls and empty them out into a sack or bag, and somebody told you, whispered in your ear, hey, Dr. Holland's only emptied out bin 5, not all the bins. Well, that's going to change your probability. And you might want to know, what's the probability of choosing a green, given that you know only bin 5 was emptied into the bag? Well, let's look at this. We take our total. Well, our total has changed. Our universe of consideration is no longer the full 20 objects. It's now just the 1, 2, 3, 4, 5 objects associated with tennis balls in bin number 5. So now that our universe of consideration has changed, we express the number of items of certain value, i.e. green, given the total number, those items that are only from bin 5. So we know we have 5 items for bin 5, so the denominator, our total, is going to equal 5. And now we look at the proportion, the number of them that are green. So we have 1, 2 that are green out of that bin, only 2 are green, so it's going to be 2 over 5, which is equal to 0.4 or 40% probability. So 2 over 5, 0.4. Okay, so this is what a conditional probability is. It's a type of filtering probability, and you can implement it that way semantically. All right, so let's look more at this conditional probability. One of the things that conditional probabilities are doing for us is allowing us to consider or even evaluate different possibilities of what happens if new information is available. So we said probabilities are based on observations. These are random variables, measurements over events, and new information, when you get it, can certainly change the probability. And we saw that when we went from looking at all of the possible bins to just bin number 5. And so it would be useful to be able to evaluate a probability that considers possible information, this idea of what happens in light of new information. And this is exactly what a conditional probability is doing. We talked about it semantically, about how you might implement it, this idea of filtering, but more logically, what it means is this idea of in light of new information. And that could be actual new information that you receive or you observe, or it could be what happens if I were to get this particular piece of new information. And so general form would say the probability of some event E given some other event A, and you pronounce that as the probability of event E given that we observe event A. And so that's what this condition variable is. It's given, i.e. imagining if you observed that event A is to be true. Now, of course, I talk about event A generally, but it could be a single event, like given that a die roll was 3, or it could be a complex event, the union of some set of events or a vector of events. And so This is immensely useful. It's used all the time in voice recognition, in autocomplete, on text messaging. And the conditional probability you're looking for voice recognition is the probability of the next word given a train of previous words, some amount or sequence of previous words. Because people just don't speak randomly, right? You speak stylistically. Certain words follow other groups of words that you've already spoken or input. In weather forecasting, you're looking at things like perhaps the probability of rain given the last few days' previous weather. In robotics, this is used all the time for localization. You're evaluating the probability of a certain location given a sequence of previous locations. And so this idea of this probability in light of new information is immensely useful across a wide variety of different types of problem domains. So a conditional probability, more formally, of some event A given event B is the probability that A occurs when B is known to have occurred. And we say the probability of A given B, and here's our notation. Now, certainly in some texts that you read, you'll say the probability of A given B. In other things that you read, you'll use this curly brace notation. It doesn't matter what the notation. What matters is that it's a condition, A given B. So this condition bar is what's important. And I'd like to note here, really, really important, that these don't have to be single events. They can be complex events. A can be a vector of events. B can be a vector of events. Okay, so let's kind of ground this out in the Venn diagram. We said the probability of A is the number of outcomes divided by the total number of outcomes that are possible. Now, the total number of outcomes that are possible, we note that as our sample space, which in some parts of the literature we call capital omega. And so our sample space omega is our universe of consideration. And without any restriction, that's going to be our sample space, all possibilities that you can have. And of course, A, when we look at this probability, is the number of desired outcomes, and it's the outcomes for which event A is true. So it's outcomes in A. As a Venn diagram here, here's our universe of consideration, sample space omega, and then we're going to carve out of that those events. It could be a single event or complex event, set of events. That's going to be marked as A in the Venn diagram. So we evaluate that, and now if we look at the probability of A given B, now we said, okay, well, given B, what does it mean to say given B, right? We're now going to change this universe of consideration, so we're going to shrink it down from omega down to this B. So now you're going to look at not just those proportion of events that out of all possibilities that are true out of your universe of consideration, we're going to update our universe of consideration to only limit to those events for which B is true, because we know given that B is true. So because our universe of consideration shrinks down to B, this denominator here is going to change. And so let's look at this evaluation. Well, the events in this new universe of consideration for which A is true, if you're limiting it to those that are in B, it's now this intersection, the probability of A intersect B, those events for which both A is true and at the same time B is true. And so you can think of this cup here, that's intersection, the set operation, and that's the same as saying A is true and B is true. Now in the literature, when you see probability of A intersect B, sometimes you'll see probability of A and B, but mostly in the literature, a large percentage of the time, you're going to see A and B written as a comma-separated list. Now, of course, A can be a single event, B can be a single event, A can be a vector of events, B can be a vector of events. It's the same treatment. And so here, we take the number of outcomes for which A is true. Well, that's the intersect region, A and B, so that probability of A and B. And then we divide that by the probability of this B region, our universe of consideration. And so this is our definition of conditional probability. Probability of A given B is probability of A and B divided by the probability of B. And this is our approach for defining what the probability of A given B is in terms of the probabilities of this intersection region divided by the proportion of probability for this limited scope universe of consideration. All right. So again, this is still just favorable outcomes. It's the favorable outcomes for the intersect region divided by the total outcomes, which is this new universe of consideration. And so when we are given B, we know the total outcomes are limited to B, and the condition then filters out of these total outcomes, right? This condition says, I don't want to consider the whole universe of consideration. I want to consider just this B region from this universe of consideration. It gets smaller, and therefore the denominator gets smaller. And this idea of new information, and it kind of makes sense, when you get new information, the chances are going to increase for the thing that you're looking for, this number of favorable outcomes, the numerator. And so let's take a look at this for some practical examples. If we have a die, and a die is 6 sides, and you have outcomes of 1, 2, 3, 4, 5, or 6 from a die roll, if we just looked at the probability of rolling a 2, well, sample space omega for a die is nothing more than the set of all possible outcomes, 1, 2, 3, 4, 5, and 6. And so with a probability of 2, well, that's just what is desired, 2, okay, there's one of them, divided by the total number, so that's 6. That's 1/6 probability. Now, if we said I knew for sure, given that it was an even, well, we're now changing our universe of consideration. Well, the evens are just the set 2, 4, and 6. And so now the probability of selecting a 2, given that it's even, the denominator changes. So the cardinality of that limited now changed universe of consideration is now 3, the number of total possibilities for even, and then the probability of 2 is just 1, so that's 1/3. So here we had 1/6, and now the probability has increased, now 1/3. The probability has doubled. Likewise, if we look at a deck of cards has 52 cards. We have 4 different card values in 4 different suits, spades, hearts, diamonds, and clubs. Now, if we said what's the probability of picking a king, well, there are 4 kings. There's a king of spades, a king of hearts, a king of diamonds, a king of clubs. So there are 4 kings available in your deck. You have a total possibility of 52, so that's 1/13 as your probability of picking a king. Now, suppose you're sitting at a poker table or playing a card game, and you want to know what's the probability of a king, but you saw the dealer hand out a jack, a queen, and a king, right? And it doesn't matter what the suits are. The jack, queen, and king, we started out with 52 cards. We dealt out the jack, and so now you have 51 cards. You dealt out the queen. Now you have 50 cards, right? 52 minus 2 is 50. You deal out the king. Now you have 49 cards. And so now, given this assumption that these 3 cards have been dealt out, you have a new universe of consideration. You now have 49 cards. Now, out of those 49 cards, you've dealt out one of the kings, so that means you only have 4 kings left. You started out with a king of spades, a king of hearts, a king of diamonds, and a king of clubs. Now, if you deal out one of them, you only have 3 kings left. It doesn't matter which one you deal out. So if we now look at the probability of getting a king, given that you saw these cards already dealt out, you're going to take the number of favorables. Well, it's going to be 3 kings that you can have, 3, divided by the new universe of consideration for the possible, that's over 49. And so this idea of conditional probability, it allows you to update your probabilities to incorporate this idea of in light of new information. And whenever you get new information, that's going to change your universe of consideration, which based on first principles, changes the denominator in this expression for the number of favorable over the total. Okay. And so we have our definition of the conditional probability, and we can take this definition of conditional probability, and we have probability of A given B. That's probability of A and B divided by probability of B. We can also write for the probability of B given A, we can write the probability of B and A over the probability of A. Now, of course, and is commutative, and it doesn't matter what order you write this numerator in the expression for conditional probability, but I like to write it so that left to right, the numerator for this expression reads the same as this conditioning. So we have A and B. A given B, we write A and B. We have B given A, we write B and A. Now I just do that. It doesn't matter. You could write probability of A and B instead of what we've written here. But I just like to write it so that left to right, it reads the same as the variables that occur in the expression for the condition. And so given this expression, we can take this first equation, and if we multiply left and right side of equality by probability of B, and we multiply by probability of B, well, the probability of B canceled in the numerator and denominator, and so we're left with probability of A intersect B is equal to probability of A given B times the probability of B. Likewise, we can do the same with the expansion for probability of B given A. We multiply left and right by probability of A, then multiply by probability of A, numerator and denominator cancel, and we have probability of B and A is equal to probability of B given A times probability of A. Now these two expressions, they're alternate expressions, and they're expressions for the same quantity, probability of A and B, which is the same as probability of B and A, right? So in the first case, we have one expansion in terms of the condition of A given B times probability of B, and we have B given A times probability of A. And so these two definitions have a name. It's called the product rule, and you can think of it as two different ways of defining what it means to say the probability of A and B. Now, the probability of A and B can be defined two different ways. One way it can be defined is probability of A given B times probability of B, and the other way it can be defined as the probability of B given A times the probability of A. Now, this is called the product rule, and it says that this is the relationship between the joint probability, A and B, and the product, or factoring, if you will, of this joint probability in terms of a condition and a marginal probability, right? A single variable probability. And so this is called the product rule. And it means that every time you see A and B, you can expand it or factor it as the product of two simpler probabilities, A given B times probability of B, or B given A times probability of A. All right, so let's look at this idea of independence. Now, independence, if we look at it in the Venn diagram, we have our events A and B, and independence means that there's no coupling between the two information-wise, and that means that they do not overlap in the Venn diagram. They share no events. And that's the same as saying A intersect B is equal to the empty set, right? So if we look at a definition for what independence is, we can define what independence means between two variables or vector of variables using conditional probability. It says that the probability of A given B, if A and B are independent, is equal to just the probability of A. So what does that mean? It says knowing B tells you no information about A. B has no bearing on what A's value is. And so if we were to do the expansion, we have probability of A given B is probability A and B over probability of B. Now, it just so happens if A and B independent, it means that the joint probability of A and B is equal to the product of the marginals, probability of A times probability of B. Okay, so if that's the case, here we have probability of A and B in the numerator. We write probability of A times probability of B. We notice that there's a probability of B both in the numerator and denominator that goes to 1, and we're left with probability of A. And so we've proven that this independence, what it means, is that conditioning on B adds no new information to what the probability of A is. All right, so let's move on to now Bayes' rule. And we said at the outset there are two different expansions, if you will, of what this joint probability means in terms of the conditional A given B and B given A. So we're going to write from first principles. So we're going to write the conditional probabilities A given B. That's the probability of A and B over probability of B. And likewise, the conditional probability of B given A is the probability of B and A divided by the probability of A. So now we know that and is commutative, and we're going to write or rewrite this probability of B given A as probability of A and B over probability of A. We can absolutely do that because you can switch or commute the operands to and, right? It's the same expression. So now we're going to write them out. Here we have probability B given A is probability of A and B over probability of A, and then that's expression 1. Expression 2, we write probability of A given B is a probability of A and B over probability of B. So for the first expression, we're going to multiply both sides of equality by probability of A. We do that, and we get the probability of B given A times probability of A is the probability of A and B. We do the same thing with expression 2, or a similar thing. We multiply both sides of equality by probability of B. If we do that, we get probability of A given B times probability of B is equal to probability of A and B. So with this, we have two expressions for probability of A and B. One expression is this expansion, the product rule, B given A times probability of A, and the other expansion is this product rule, probability of A given B times probability of B. So we know that the right-hand sides of equality for both expression 1 and expression 2, they're the same. It's both probability of A and B, so we can absolutely mathematically equate the left-hand sides of equality with one another. And so we do this equation, we equate this left-hand side with this left-hand side because that right-hand side is the same as that right-hand side. So we equate the expression 1 with expression 2, left-hand side of equality equated with left-hand side of equality, and we get probability of B given A times probability of A, that's from expression 1, is equal to the probability of A given B times probability of B, that's from expression 2. So equate them together, and then now we're going to divide. We're going to divide both sides of equality by probability of A. If we do that, well, this probability of A on the left-hand side is going to cancel, and we're going to be getting this right-hand side of equality. That's going to be probability of A given B times probability of B divided by probability of A. And we're left with this expression. Now, this expression, if you look at it, it's a way of defining the probability of this condition on the right-hand side in terms of this condition on the left-hand side. And so, in essence, what we have is now a formulation of what it means to calculate probability of B given A using information about the probability of A given B. So, in essence, we're changing what the condition variable is or vector of variable is. Now, this has a name. It's called Bayes' rule. And what Bayes' rule does is it connects the expression involving two different conditions. You're defining what it means to say given A in terms of given B. Now, this is useful if you have one piece of information, but you want to evaluate a question or probability. What is going to happen? What is the likelihood if I observe a different observation or have a different piece of information A? So what's the likelihood of B if I observe A? But what if you only observe B? How do you express this if I observed A? And this is immensely useful if you have one piece of information and you want to evaluate a question concerning a different piece of information. And this is used all over the place in classification, in robotics, in clustering, lots and lots of applications for this. But we're going to consider this as a way of defining a classifier. But before we can talk about that machinery of defining a probabilistic classifier, we absolutely have to talk about what conditional probability is and what Bayes' rule is. Okay, so one of the things you'll notice here is this denominator. It says probability of A, but you said that, oh, well, what if you don't observe A? So we're going to use this idea of total probability with a special construction to now take care of this denominator. So we have everything in the denominator is defined on things pertaining to observations of B. All right. And so before we do that, let's go through an example of Bayes' rule, and we're going to show that you can get the same result using this Bayes' rule, but we're going to show it directly first using conditioning, and then we're going to use Bayes' rule to get the other condition and verify that it's the same result. And so we have, in this example, 90% of the flights depart on time, and then we also have 80% of the flights arrive on time. And so let's have the event A is the event for arrival on time, and D is the event for departure on time. We also have 75% of flights depart on time and at the same time arrive on time. So that's what you want. That's the optimal I know for flight. But just because you arrive on time doesn't mean you depart on time, and just because you depart on time doesn't mean you arrive on time. But in this case, 75% of the time, the flights will both depart on time and arrive on time. And so from our definitions, arrival on time, probability of event A is equal to 0.8 for 80%. Probability of D for departure is 0.9. And then the probability of A and D, that's arrival and departure, that's going to be 0.75 for 75%. So let's now look at the probability that a flight is going to arrive on time given that it departed on time. So that's probability of A and D over probability of D. All right, A and D in the numerator, that's 0.75. Probability of D depart on time is 0.9. That's 0.8333. That's 83.33%. Probability of departure given that it arrived on time, well, this probability of D and A depart and arrive on time and is commutative. So that's 0.75 in the numerator divided by probability of arrival on time. That's P of A. That's 0.8 as defined, and that's 0.9375 or 93.75%. 93.75% probability. 93.75%. Okay, and so what we're going to do then is now use Bayes' rule, and we are given probability of A given D. We calculated that was 0.8333, and now we're going to use Bayes' rule to compute probability of D given A, not directly. And so we want to know, imagine the probability of D if you observe that it arrived on time is nothing more than application of Bayes' rule. So probability of D given A is probability of A given D times the probability of D over the probability of A. Now, A given D, well, we already did that. That's 0.8333, so we write that down, times the probability of departure, that's 0.9, multiply 0.9, divide by probability of A, that's 0.8, that's 0.9375. That's exactly what we had before when we computed directly probability of D given A. Now, that probability of D given A required us to observe A, but in this case, we observe D and not A. And so this is just to demonstrate that Bayes' rule actually does work. All right, so let's look at this total probability. And in this, we're going to take a little bit of time to explain construction. And in this construction, we have our sample space omega. That's this yellow box here. And we're going to take our sample space omega, and we're going to cut it up into a partition. Now, it doesn't matter how many slices we have in a partition. Let's just say we have k many slices. So we have B1, that's our first slice of our partition. We have B2, that's our second slice, and all the way up to some number k of slices. Now, it happens that each one of these B slices, and there are k many of them, they're non-overlapping. And because they're non-overlapping in our sample space omega, they're going to be independent. And moreover, not only are they independent, they are also what are called collectively exhaustive. And so if I take any two arbitrary slices, B slices, from my partition, I call the first one my ith and my second one the jth. Because each one of these B slices is non-overlapping, we know that Bi intersect Bj is equal to the empty set. So that means they're independent or mutually exclusive. Now, because you notice each one of these k many B slices gives you the full representation of the entire sample space omega, we call this collectively exhaustive. Now, these two properties together, collectively exhaustive, says that the union of all the B slices is exactly equal to the entire sample space omega. So that means all of our B slices, we put them together through union, and we get the entire set of all possibilities, our universe of consideration. Now, mutually exclusive, it means that if you're not talking about the same B slice, the ith and the jth, their intersection is empty set. So that means they are independent from one another. So we have this property associated with these B slices. They're pairwise independent and collectively exhaustive. So what does this mean? It means we can use them to deconstruct an arbitrary event. So let's take event A, and we're going to take A, and we're going to look at the intersection of event A. It could be a complex event or a vector of events with all of these B slices. So you're going to intersect it with the first B slice, the second, the third, the fourth, etc., all the way up to and including the K. Now, if we were to do that, each B slice, when we intersect A, it'll perfectly decompose A into pieces that are non-overlapping with one another. So if we were to do that kind of logically, well, there's one part of A intersected with a B slice. Here's another part of A intersected with a B slice. There's another part of A intersected with a B slice. Well, here's another. Here's another. Here's yet another. Here's another, that little sliver on bottom. And then here's yet another here in the center. And so each one of those pieces is A, the result of A, intersected with one of these B slices. Let's just call that B slice I. And so some part of A will exist, or piece of A will exist in each one of these B slices if we intersect the entire set of K many B slices with our complex event A. And as such, because the B slices are collectively exhaustive, we know that it doesn't matter what A is, all parts of A will be represented because all those B slices give you the entire universe of consideration, our sample space omega. And we also know those parts of A, deconstructed by intersecting with each of these B slices, they're independent from one another because each one of these B slices is non-overlapping. They are independent from each other. And so here, whenever we do this construction, we can define A as just the union of its intersection with the first, the second, the third, and each of those K many B slices. And therefore, if we look at the probability of A, the probability of A is built up as the probability of each one of these independent B slices. And because they're independent, we can just add them up. So the probability of A is nothing more than the sum for J goes from 1 to K, because there are K many B slices, of the probability of each one of these intersections between A and that Jth B slice, where J goes from the first one up through and including the Kth one. And so this is the law of total probability. And we can use this law of total probability to change the denominator in Bayes' rule for a full consideration of Bayes' rule, not considering the condition variable when we change it. So let's talk about this. So we have this partitioning of event A using this mutually exclusive collectively exhaustive set of B slices. And if we have two B slices, what does that mean? So here's our universal consideration. We have the first B slice, B1. Let's just call it B. Our second B slice, let's call that B bar, since it's just two of them. And now we have some event A. And so given this construction here, we say we can make the probability of A by summing up A intersected with each one of the B slices. Well, now for this expression, that's the same as probability of A and that J B slice. Well, we just got done saying, all right, well, we can use the product rule. And so applying the product rule, we then take this joint distribution, A and B sub J, and we apply that product rule, and we get probability of A given the Jth B slice times probability of the Jth B slice. Because remember what the product rule says. The product rule says the probability of A and B is equal to the probability of A given B times the probability of B. And recall, we got that from the definition of conditional probability, which says the probability of A and B over probability of B is equal to probability of A given B. So this is just a substitution of this intersection of A with each B slice, applying the product rule, where this is our product rule. So we can rewrite this term inside the summation as the probability of A given the Jth B slice, Bj, times the probability of Bj. And so if we have K is equal to 2, this probability of A, if we have two B slices, is equal to the probability of A given B times probability of B, that shouldn't be B bars, that should be of B, times the probability of A given B bar times probability of B. Let me rewrite that. Probability of A given probability of A given B times the probability of B plus, because it's a sum, K goes from 1 to 2, J goes from 1 to K, or 1 to 2. The second term, probability of A given B bar times the probability of B bar. Now I'm just calling the first B slice B and the second B slice B bar, and this is our A. And so this term here, that's our first part, and this other term here, that's our second part. Okay, and so this is a definition for A. So let's now go back. We can take the product rule that we talked about, and we can apply the product rule for the first term, that's A given B, and we can apply the product rule for the second term, that's A given B bar, which is exactly the sum for J goes from 1 to 2 of the probability of A intersect with Bj. Okay, and that's exactly our total probability. So this total probability gives us a way of deconstructing an arbitrary event into the sum of non-overlapping parts, the sum of independent parts through union. All right, so now we take our Bayes rule, and we set our Bayes rule, probability of B given A was equal to the probability of A given B times the probability of B over the probability of A. Now, in this case, we said we were conditioning on A, but one of the things that kind of didn't set well was this denominator is the probability of A. We want to kind of fix that up, so we're going to substitute in what it means for this example where there are two B slices for K equals 2. We're going to substitute using law of total probability for this denominator. So if we do that, we're going to write in this denominator now becomes probability of A given B times probability of B plus the probability of A given B bar times the probability of B bar. And you notice here on the left-hand side of this expansion Bayes rule, we have given A, but you notice here we say given B, probability of B. We say given B, probability of B. Given B bar, probability of B bar. Now we've eliminated all mentions of given A in this denominator. And so we're now using only observations of B or observations of B bar. And this expression is the full treatment of Bayes' rule. Okay, so with that, that's all I had. And we will end there. Again, please make sure you start the midterm today, right now. I look forward to presentations a week from now, but that's all I had to say today for conditional probability. Until next time on Thursday, as usual, please stay healthy, please stay safe, and I will see you all on Thursday.